Mr. Jonas Mota.
Muito prazer.
Nice to meet you. Good afternoon, everyone. Can you hear me well? I'm going to start presenting an important piece of information from Speak to Talk because I'm kind of nervous. If you don't understand me, please let me know and I'll come back and explain. I'm Jonas. I worked in the development of products and processes at BASF. I'm responsible for the products applied in construction. That's what we're talking about here. And I focus on sandwich panels by continuous line. Explain. If you don't understand, please ask me. You can ask questions in the end, as you wish. Just to start, first of all, I'm going to talk about BASF performance materials. That's where polyurethanes are located. That's that's our expertise. In our business unit, we have a couple of segments that are here. Laser doesn't work very well, but you can see these segments. Talking a little bit about polyurethanes, the appliances, freezer, fridge for thermal insulation polyurethane, furniture, they are for mattresses, chairs, pillows, rigid, flexible foams. Automotive, all the materials applied in automotive, flexible on the seat, glass, encapsulation. Another area that is new, electrical cars, elastomeric material, polyurethane for the batteries, but for mobility, electrical mobility. So footwear, soles, all the parts of shoes made of polyurethane. And the market we're talking about, civil construction, all the materials applied in civil construction are thermal insulation by spray, continuous process, blocks, SIP that our colleague from Senai just talked, adhesive, permeable, impervious flooring, all the polyurethane products for civil construction. As you may know, but how many applications there is, polyurethane is very versatile. We can do several things with only two components, polyol and isocyanate, and we make several types of products with different properties, different processes. Our market, not BASF and performance materials, have over 60 years of experience working in partnership with the customers. The idea of work of BASF is to deliver to the customers a customized solution in co-participation. It's not BASF imposing anything to the customer. The customer talking to BASF, showing the niche of the market, the processes, and then we participate together from the idea to the execution until we have a final solution. So this is how we work. We have over 60 years of experience working like that all over the world. That's why these are our plants in the world, performance material systems. We produce isocyanate. You can see it's very scattered. These are solutions that are customized, solutions that you have in Europe. Sometimes it's a solution for us, but it has to be adjusted for the Brazilian market, different climates, different temperatures. So we are scattered in Brazil. We have two systems, houses, one in Guaratinguetá between São Paulo and Rio de Janeiro. The other one is near Buenos Aires in Bursaco. For South America, materials come from here. They are developed. There is a development center in these two places. In São Paulo, our development center is in São Bernardo do Campo, and productions are made in the city of Guaratinguetá. So this is where the products come from. And then we have to think about sustainability. BASF is thinking about that. We have been working a lot in making it sustainably, working sustainably, using the resources, better processing, to work sustainably, producing something that we can use, our customers can use in a sustainable way. Things with less processing will last longer. To eliminate as much as possible losses, and in the working life of the product, how to recycle that.
So we've been working on global projects to make something that is less aggressive or is more sustainable, so that when we use it and process it, it is more sustainable and we can recycle it by a number of means. It could be physical, chemical. And I'm now going to talk about our topic that brings us here today, Elastopir New Generation, which is a product for sandwich panels for facades. These are architectural panels. The idea is to explain some topics to you. We're going to start with an explanation of what sandwich panels are. I'm going to explain what the continuous process is and why it is continuous. The focus is to apply it in a process continuous. So a sandwich panel is made in a continuous process. Many of you know that, but other people will be discovering this. What are the solutions BASF offers? And then we're going to start talking about panels applied on facades and the main problems involved. We're going to try and understand where the problems come from, what causes the problems, and then we'll begin talking about Elastopir, our solution that we're bringing before you today. So, talking about the sandwich panels, basically they are sandwich panels. The name says so much. You have a metal plate one side and on the other side, and then you have an isolating core. This could be EPS or mineral wool, PUR, PIR, a number of things. I'm going to talk about polyurethane in this context. And so it's a sandwich with metal slices of bread and a filling of PU. And there are a number of joints and adjustments, different types of dovetailing and fittings. Here we see a number of different types of panel and the versatility of the different colors and models, and the different types of profiling. And to talk about the profiles, we can make micro-ribbing or micro-V sinus corrugated trapezoidal. These are architectural models, so they're more, let's say, beauty than technique. And then now the continuous process. With all the panels that we've seen, they can be processed on a machine such as this. There are a number of ways of producing this, sandwich paneling. It could be continuous or non-continuous. Do you make a block and then do you cut it up or glue it? But what about why it's continuous? Everything starts here, which is the unspooling of the steel. Then you place the steel coil here, it starts to unspool, and you have one plate above, one below, making the sandwich. Then you go through this next station, which is profiling, where the panel is profiled, whether it's ribbed or sinus wave. So it goes through that step. Then you come to an area, you see this photograph, which is preheating and adhesive dosing. The idea is to heat the plates and to keep them at a stable temperature above and below, so that later on we're going to dose the polyurethane into the gap. Then this little house is the polyurethane doser. I don't have a photograph showing that, but there will be a bit later. You dose the polyurethane onto the lower plate, and then they go into the press. The press is basically the oven for our cake. It's responsible for the cure step for a few minutes until it's cured, and then at the end of the press, that last photograph, it will be coming out at the right thickness and width with the cured core, and then it comes into this other area, which is the cutting or sawing area. You cut them at the length and size that you wish. From here to this point here, it's continuous. Basically it unspools and the plates, and they only cut when the sandwich panel is ready. Then they are piled or stacked for cooling in this cooler, this area here. The panels are pressed together and it's heated, and polyurethane releases heat. The panels are extremely hot. If you piled them one on top of the other without cooling, what would happen is that they would very likely buckle or wave or wrinkle, and they have protective film that would probably melt and then stick, and you wouldn't be able to separate them from their stack. So go through the cooling, go to the stacking, stacked up. It's a logistical issue, it depends on the truck, and then you come to the packaging area, the packer. So you wrap stretch film around the packages. That's the continuous process, and now I'm going to present you or introduce the products to you. The first one is an old one, PUR. It's extremely stable. I think it's the most stable in Latin America, at least, of continuous panel production. For facades and all, it could be 20 to 200 millimeters. Surface quality, good. At the end of the day, it's PU, but the only disadvantage is precisely because it is a PUR. It's a B3, according to the fire brigade. It doesn't. It was first of all classed as class 6. These panels cannot be applied in certain applications in accordance with IT10. If we don't need any fire retardants or resistance, then, for example, low temperatures, processability, there's a line. This is the best material, and you can really test the materials, and the material is as robust as you can find. Then we move to Elastopir 1132. Which is made, it's a polyol for polyisosanurate, which has greater fire resistance. It's 1132/500. It's a replacement of the other one I just mentioned. If you need good fire resistance, this is the one for you. It's very sturdy and has all the properties that you want. It attains all the national or domestic and international fire retardancy features. And something to highlight, this can modulate in terms of density. We can have a standard density about 40, 42. And if it's an application where you need to reduce density because of cost benefit, it can be produced down to 30. But for 30, we need to look at our process. It's not just the material. When you reduce density that much, you need a very stable processing. But this material is the next generation of PUR. It's a sturdier PIR, and we're approving it for use in with clients. It's 1139-504. It's also very flexible in terms of density. And what we did here is we changed some of the raw materials, so we have more modern ones. They've recently arrived on the market, and in the tests we found a better compression strength. And if you want to reduce density, usually density has a lot to do with compression strength. Compression strength tends to fall with reduced density. So even at lower densities, in the case of the chance of having a panel with better quality is very high with this product. And the idea of BASF, if you already are a client of ours, it will replace the previous one that I showed. And that's it for that material. So now a little bit about our portfolio.
All those products I talked about were developed and produced in Brazil or in Argentina in South America. And we have the last global launch product developed in Europe and launched in the European Trade Fair, Elastopure Blue. It's better lambda, better U-value, better efficiency, better thermal insulation, and Elastopure that delivers the best thermal insulation. And what is the concept of the material? If I have a slaughterhouse and I need 100 millimeters to reach the insulation that I need, this material insulates more than the common ones. Could be 70 millimeter panel, 80, talking about non-official figures. It's just an example. Then you decrease the thickness of the panel, you save a little bit of material, and you have internal space. That's the concept of Elastopure Blue. It insulates better than the other ones. Talking about sustainability, we've launched in the last trade fair Elastopure Biomass Balance. Elastopure is what we have in the market today, deliver the same properties, processing, same material, don't need testing. For the customer who is asking for lowering carbon footprint, it has the best material. If you have any queries about these materials, come to our booth. We're going to explain all that. The marketing team is here. Sustainability team is here. Talking about what we came to talk about, facade wall panels. It's architectural, so the architectures love wood, dark colors, blue. This is the challenge of the wall panel because it's architectural. It has to be beautiful. What's the issue? Bubbles in facades. This happens all over the world, very common, blisters. But because it's an architectural panel, last thing that could happen is to have a blister. Because the end consumer bought a blue one, did a wonderful bazaar, there are 6 blisters, they're going to complain. Then the panel maker will have to assemble again, put another one. So it's a nightmare of the panel makers. And what did BASF do? Because it's a global problem, We started investigating that. Of course, it was on purpose, not 100% of the cases. 90% the blisters are near the the fittings. Between one panel and the other, you see the blister. There is a failure or a weakness in fitting the panel. And so there is a predictive study why it always in the fittings. There are some explanations. A wall panel has this fitting that is longer to close the screw that fits it. So you fix the other panel comes from the top, this part, and for it to be beautiful, for the screw not to show. So this is a critical part. What happens? BASF tried to do a prediction. They looked, and it indicated we had a study of curing temperature. At curing, the darker, there was more curing. Temperature was greater. Polyurethane has cured. The bluish colors, that's where the temperature was not up so high, there wasn't ideally cured for polyurethane. Because it's a very small area, we usually dose material here, and material needs to expand and fill that. When doing that, the material generates turbulence here. There is an accumulation of material. There could be bad mixing here. That's why we see that curing is not perfect, and there it's a real case. This is a prediction. This is a real case. There is a dark color inside the foam. That's curing. It's not the best foam possible. In that spot, it's bad. There was a warpage study, which is the critical area. Why warpage? When you fit one panel to the other, you match the plates. The first part that hits is this bit. So one plate hits the other. This is the thinner part of the panel, it moves. That's a warpage study. The most critical point is this one, and it's where the blisters start showing. So when we are assembling it, you move this bit here, this part, this fitting, to close, so the foam is loosened. There is no problem. People finish assembling, but this is the space where the PU loosened or was detached. So the gas in PU goes out and it goes to the easier place. This is the easier place. It's open. The rest of the panel is glued. So it stops there. It heats up and cools down. So this is the fitting. The next one, you will see where the wall panel happens. The wall panel is on the outside. So it suffers with rain, cold, hot weather. We did a simulation. That's the outside the panel exposed. This is the inside. We simulated raising the temperature from 10 to 70, 10 degrees to 70 in 10 minutes. It's not crazy. It's not a big stress. I've seen panels in dark gray in the northeast reach more than 100 degrees in less than 1 minute. If there is if the sun is out, it will heat up. If the sun is behind a cloud, it will cool down. So the temperature hits here, the temperature cannot go down here, so the plate inside doesn't modulate. The plate on the outside dilates and contracts according to the temperature. The greater the temperature, the greater the dilation. Thin plates and very dark plates tend to show more issues. If there is heat, the little gas that stays in the previous slide, it was the tear. The gas went there, the sun heated up, the gas goes out, the blister shows the plate is moving. So there can be other issues. Waving, sometimes you see on the wall panels, I look at all the wall panels I can see. You can see the waving. The panel finishes detaching, then the blister will show. So related to metal, application, the temperature, other issues that may happen. The problem is the blister. We're talking about several factors for the blister. One is the fitting, the other one is temperature, color, and processing. What is overpacking at joints? You place too much material, the material will fill that, it will be accumulated, and it finish curing. It doesn't cure well, then it detaches. And little by little, it opens a crack.
And this tears the plate off the PU. There are some techniques in production that can minimize this. It's minimize. Poor adhesion could be plate quality, primer quality, preheating. These things could cause it. Corona effect. But for elastopir, it's mainly the adhesive. We need to put the adhesive on the lower plate. And we can have, for example, with adhesion problems happen if it's been badly distributed. A lot of problems because of the actual quality of the foam. Poor mix, if you're dosing and you see some threads of different materials, then that means you have an incomplete reaction in the foam. You don't have all the properties it should have. And here we see a poor flow because of second reaction. Second reaction is the PIRS. It's very hot material. You get a second reaction on top of the first reaction. It's a little bit technical, but it's important to say that it does happen. And the reason is it was on these points that we worked in order to deliver a solution. BASF cannot affect, for example, the fitting. Where we are able to act is with regard to formation of bubbles and the particular foam problems. What did we do? We lowered the viscosity. So substances whose viscosity is very similar mix better. Either low viscosity or very similar viscosities. We improve the mixture. Small cell size, smaller than usual compared to the standard elastopir. How do they help small cells? Imagine a room with a 10-meter space, and you place okay, if you've got a roof which is 10 meters across in span, but you have walls or partitions at every 2 meters, it's better supported. The gas is kept inside the roof space, and gas does not escape so quickly. So if you reduce the cell size, making it smaller, that's better. And also lower the BA, so if you put less gas, you'll have less internal pressure and improve fluidity. So you can fill the space and you don't get the non-fitting at the foam failure point with less turbulence. better flowability, in other words. These are the points we changed. We've tested the material, and it's already being used in the largest panel makers in Latin America. These are very standard results. We had a very good tensile strength. People who thought it was the foam. Compression strength also well above 100. The numbers here, the figures are the minimum benchmarks, the minimum reference points that the market demands. And the material passes the ignitability test. The next test is in the construction business, so foam enables the customer to achieve classification 2A, which for our fire reaction test, at least in the state of São Paulo here. This is the name of the new product. It's called Elastop 1132 over 502, stroke 505 and 2. It's for facades. I'm not promising there won't be bubbles, but it's really mitigated the bubbles issue. It's not only a product issue, and it reduces the number of bubbles in facades and attains the mechanical properties the market demands. Above all, the customers that we have served to date, complaints of bubbles have dropped. We haven't had problems with customer complaints. Automatically, there's less residue then. With a smaller cell size, we have a better thermal isolation result, so the lambda is better. It's not the same as Elastopure Blue, but it's still very, very good. And with regard to fire safety, it passes and meets the domestic and international fire reaction requirements. So as I said, this was new material. I'd like to leave you my contact details. Any queries, if you want to come along later to our booth, the whole BASF team is there, and you can send me a question on WhatsApp. I'm happy to answer your questions. Any questions from the audience?